we will be given an input which has n, which represents the number of vertices. We will be given edges between two nodes, and this tree is supposed to be a undirected graph. What that would mean, that let's say you have 0 comma 1, so a edge exists between the vertex 0 and the vertex 1, which basically represents that a edge will also exist from 1 to 0, because it's going to be a undirected graph. And given a undirected graph, we have to figure out whether it is going to be a valid tree or not. And we can say it's a valid tree based on two conditions. The first condition is that from any node in the graph, any vertex that you have within the graph, you should be able to reach any other vertex in the graph that is given to us. So there should be no disconnected components within the graph. The graph should be connected as a whole, and there should be no cycles in the graph that you have. And if two conditions are met, then we say it's a valid graph tree. Now that we have understood the problem statement a bit more, let's dive into the solution. First thing we said is that we should be able to reach all the nodes from a specific node in the graph. So if I start at 0, I should be able to reach 1, I should be able to reach 4, I should be able to reach 2, 3, all the nodes. And to do this, that's where the depth first search traversal comes into play, wherein we will start from the root node, which is going to be 0 here, and then traverse all the way and make sure that all the nodes are getting visited. That's step 1 of it. And to do that, we're going to first build a adjacency list. This adjacency list is going to be the graphical representation of the input that we are provided. And from that graphical representation, we will then do a depth first search traversal. First step is going to be building an adjacency list. Why do we want to build a adjacency list? Is because we want to make a graphical representation of the vertices that we are given and be able to traverse them in a depth first search fashion to see if from any node you can reach other nodes that are there in the graph that you are given or not. And the adjacency list, which is the graphical representation, will look something like this. We'll have 0, 1, 2, 3, and 4. Now we say 0 is going to 1, 2, and 3, and that will be represented as 1, 2, and 3 here. 1 has an edge going to 0 and 4. So it's just going to say 0, 4. 2 has an edge going to 0 because it's going to be an undirected graph. And 3 has an edge also going to 0. 4 has an edge going to 1. And that's how this adjacency list representation is going to look. The step 1 that we said is going to be building this adjacency list. So build the adjacency list that we want. And to do that, I will just say let adjacency list be a new map. And what we are going to be given is the number of edges and the vertices that we have. And to build this adjacency list, I will first initialize it in the map. That will look something like this. I will just say I going from 0 up to n. I will keep doing I++, and within this loop I will say adjacency list dot set against the I value a empty array. Then I will populate this relationship that we are maintaining by going through the edges that we have received. And to do that, I will go from I up till the edges that I have, and within this I will assign values corresponding to the vertices, and those values assignment will look something like this. We will just say this list dot get the first vertex. So we have two vertices. This is vertex 1 and this is vertex 2. Get the first vertex that you have received here within your I, and against that you push the second vertex. That means an edge exists between this two vertices, and that will just say push. We are pushing by reference. First we get from this map, then we have the reference. Against the reference we just push, and to push we will push the second vertex that we have received in the input. That is going to be this value that you have. So against this value you push this value, and similarly against the second value you have to push the first value because this is undirected graph. and we will do the exact same thing for the second aspect, which is going to be for the edge, put the first value, and this is going to build us the adjacency list. Now that we have built the adjacency list, let us proceed ahead to the next step, that is doing the depth first search traversal. We will travel in a depth first search manner such that we want to make sure we are able to reach all the nodes that you have. What are the nodes that we have? We have 0, 1, 2, 3, 4, which is indicated by number 5. So we want to reach 5 nodes that are given to us. And how will we do that? I will start from the 0th node here. I will say 0, put it in a seen list. So I will maintain a list of nodes that I have visited, and within this list I am going to keep on adding whatever vertex that I am encountering. So I have seen 0, and for 0 I will, once I have put it in my seen list, I will go to its neighbors. The neighbors are 1, 2 and 3. So from 0 I then go to 1 via a depth first search traversal. I put 1 in the list, saying now I have seen 1 also, and then for 1 I see what are its neighbors. 1 has 0 and 4 as its neighbors. Now 0 we have already seen, we have not encountered 4 yet, so I will go to 4 now. I will say 4 has been marked as visited, and from 4 there's an edge also going to 1, which is already visited, so I don't go through it again. Then I come back to this level. I see what was the next neighbor. The next neighbor was 2. I go to 2. I put 2 in this list. From 2 I see what are its neighbors. It has 0 as its neighbor, but 0 has already been visited. Then you come back, then you go to 3. You see what are the neighbors of 3. 3 has 0 as its neighbor, 0 is already visited, and I build this depth first search traversal from my 0th position, and I have all these vertexes that are in the set. Now I will just check what is the length. So I have 1, 2, 3, 4, 5. I have this 5 unique nodes in my list that I'm keeping track here, and the n value that I received was also 5. That means I'm able to visit all these unique nodes within my depth first search traversal, which satisfies our first condition that says from any node you should be able to reach other nodes in the graph that you are given. And in terms of code, that will look something like this. First we said we will be having this depth first search traversal. So I will build a depth first search traversal which will pick a node, and within that node I'm going to keep a tracker of whether the nodes have been seen or not. And to do that I will just keep a set here which is going to basically represent whether the unique node has been visited or not. And if I have already visited the node, then I don't need to revisit it, because then it's just going to cause repetition. And if you have not visited it, then you just mark it as visited. I will just say scene.add whatever node you are currently at in the sequence of the first search traversal, and then I'm going to visit its neighbors. And to visit its neighbors, I'm just going to go from the graph that I have built of adjacency list dot get for that specific node which you are currently at. We will just do a depth first traversal in a recursive fashion for the next node that you have encountered. And then similarly from 1 we will go to the next node, which is going to be 4, and then it's going to just backtrack once the node has already been seen. And this will get triggered via the root node. So we will just say do a DFS from the root node that you have and keep filling this list which you are keeping track of, which is going to be the unique set representation that we have here. Once we have completed step 2, what is going to be the check that we do? The check we are supposed to do is just to make sure that if there are 5 unique vertices, seen all those 5 unique vertices, because that would mean that from any node you can visit other nodes that are given in the graph to you. And that check will just look something like this. So if the scene.size that you have is equal to the number of vertices that you have received, that would mean that the condition 1 is being satisfied and it is going to be a valid tree. And that covers the depth first search traversal aspect. There has to be no cycle in this undirected graph. Now, how can we find out whether there is a no cycle in this undirected graph? We will be using the graph theorem to make sure that there is no cycle in this graph. And the graph theorem says that if you have n nodes, then you should be having exactly n minus 1 edges, which will mean that there doesn't exist a cycle in this undirected graph and it is valid. That representation comes from the graph theory. Valid tree with n vertices has n minus 1 edges. And let's quickly see how this theorem works and then come back to our solution. The graph theorem will first assume a base case that will say that if you have n as 0, so you have 0 vertices, which will mean that you have 1 minus 1, which is going to be 0 edges. Then it says if you have n equal to 1, you have 2 minus 1, which gives you 1 edge. Then you say n equal to 3, you have 3 vertices. You say 3 minus 1, which is giving you 2 edges. From this base case that we have, we will go on to the next step now, which is going to be a hypothesis. Do a induction hypothesis, which says that going from 1, 2 and 3, only for up to 3 we said it's going to be valid that you are going to have n minus 1 edges. Then we have a very high value of this number of vertices. Let's say it is n. We don't know whether for n we have n minus 1 edges or not. That is something we are supposed to prove. So let's pick up a value m, which is going to be somewhere between 3 and n, which is not exactly going to be equal to n, just 1 less than n. And let's assume until this value the theorem holds true. Let's say m nodes, it's going to have m minus 1 edges. M nodes representing m minus 1 edges. So we make this induction hypothesis as the second step. The third step, or induction step. Now, what does a induction step mean? For any tree with n nodes, remove a node with a degree of 1. Let's consider a leaf node and say this has n nodes. For this n nodes that we are given, we will just consider a leaf node. And we are saying this is a valid tree with no cycles in it. And the leaf node we will just remove from this. For now, we are saying that this node that you had, which was the leaf node, gets removed. So first you had n nodes, now you are left with n minus 1 vertices. Because you had first started with n vertices, now you are left with n minus 1 vertices. Now let's say, because we said up to m we held the theorem true that m nodes is going to have m minus 1 edges. Now n minus 1, which is basically n minus 1, becomes m, and m has relationship that m nodes will have m minus 1 edges. And if this holds true, mean that it will have n minus 1 minus 1 edges, which represented as n minus 1 minus 1, which is giving us n minus 2 edges. So this gives us n minus 2 edges. Now when we have n minus 2 edges with us, first step was we removed the node. Now let's put the node back. As soon as you put the node back into the tree, now you have the node again with you, which will just increase the number of edges you have. One more edge to it, which will then add a edge representing n minus 1 as the final value of edges that you have. And come to the conclusion that if you have n nodes, you should have exactly n minus 1 edges for the graph to not have any cycles and it to be a valid tree. And that we will just now represent within our tree itself. So we will check the number of edges that we have received. We received 1, 2, 3, 4. For edges that we have, vertexes we have 5. So 5 and then this is represented as 5 minus 1, which is giving us 4. So exactly n minus 1 edges, which is n minus 1. And now let's just convert this into code. We said that the edges we have has to be exactly n minus 1, and if they are not, then we will say this is not valid. And the comparison happens with edges dot length has to be equal to n minus 1, and if this is equal, that means it is going to satisfy the condition 2. But if it is not equal, that means it can never satisfy the condition 2. So no point checking condition 1, because both the conditions have to be met. And that's pretty much it in terms of implementation. Let's compute the time complexity and space complexity involved now. For the step 1, that was building the adjacency list that is given to us, we are going through all the edges. So let's say the time complexity for that is going to be big O of E, where E is representing the number of edges you have. Then you have this depth first traversal that is happening, which go through all the nodes in the worst case. And the time complexity involved there is going to be big O of N. So for big O of E edges, then you do this big O of N depth first search traversals, which gives us a time complexity of big O of N plus big O of E. So let's say the time complexity that we received is going to be big O of N plus big O of E. But we also went through the graph theorem, which told us that for a valid tree with n vertices, it has exactly n minus 1 edges. Because of this, when we say that V is the number of vertices that you have and E is the number of edges that you have, in this case, the length of this edges is going to be exactly V minus 1, which has this 1 as constant. So we can say it's somewhat equal to E itself. This becomes V plus V, which is 2V, and number of vertices is going to be N, and let's say it's 2N, and then 2 being the constant, you're left with N. Hence the time complexity is big O of N. And similarly, in terms of the space complexity, also the space is going to be occupied by this adjacency list is also going to be occupied by this scene set that you have. For the adjacency list, it depends on the number of edges that you have, and for the scene list, it has vertices that you have. So that also becomes big O of vertices plus edges. And we said vertices and edges are almost equivalent, and then we follow the same rule wherein vertices plus edges becomes big O of N itself, and that's why the space complexity is also going to be big O of N. Thank you for watching. Please like and subscribe.